เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้าวิทยาลัยเพื่อการค้นคว้าระดับรากฐานสถาบันสำนักเรียนท่าโพประกาศจัดตั้งขึ้นเมื่อวันที่ 14 มีนาคม พุทธศักราช 2554 รับรองสถานะโดยสภามหาวิทยาลัยนเรศวรให้สถาบันสำนักเรียนท่าโพสำหรับฟิสิกส์ทฤษฎีและจักรวาลวิทยาหรือ TPTP ซึ่งแต่เดิมนั้นดำเนินการภายใต้จิตอาสาของเหล่าคณาจารย์ฟิสิกส์มาสเตอร์ทัพพาเอียนตั้งแต่แรกเริ่มเมื่อวันที่ 8 สิงหาคม พุทธศักราช 2539 ต่อเนื่องยาวนานจนเป็นสถาบันแห่งการผลิตผลงานศึกษาวิจัยและเป็นอาสมบ่มเพาะนิสิตสาขาวิชาฟิสิกส์ทฤษฎีให้มีความรู้ความเข้มแข็งทางวิชาการจนได้รับการยกสถานะให้เป็นหน่วยงานระดับคณะวิชาอย่างเป็นทางการถือเป็นการประกาศเจตนารมณ์ผลักดันยุทธศาสตร์พิเศษของมหาวิทยาลัยนเรศวรที่จะก้าวเป็นมหาวิทยาลัยวิจัยชั้นนำของประเทศในระยะเวลา 10 ปีที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตผลงานต่างๆมากมายผลงานวิจัยตีพิมพ์ระดับนานาชาติจำนวน125บทความผลงานวิจัยตีพิมพ์ระดับชาติจำนวน8บทความงานประชุมวิชาการระดับนานาชาติจำนวน7ครั้งงานประชุมวิชาการระดับชาติจำนวน10ครั้งการจัดอบรมเชิงวิชาการระยะสั้นและโครงการบริการวิชาการจำนวน58โครงการการจัดสัมมนาวิชาการ200ครั้งคณาจารย์ของวิทยาลัยได้รับรางวัลเชิดชูเกียรติทางวิชาการจำนวน15รางวัลบันทึกข้อตกลงความร่วมมือกับสถาบันชั้นนำอื่นๆจำนวน13สถาบันหนังสือและตำราวิชาการจำนวน13เล่มวิดีโอสอนออนไลน์ผ่าน IF Channel จำนวน34วิดีโอนอกจากนี้ CQuIC Consortium ได้สร้างเครือข่ายความร่วมมือทางวิชาการระหว่างสถาบันฟิสิกส์กว่า20สถาบันกลุ่มเครือข่ายพิษณุโลกฟิสิกส์เน็ตเวิร์กได้ส่งเสริมกิจกรรมสัมมนาวิชาการในจังหวัดพิษณุโลกและสถานีฟิสิกส์ศึกษาคือการให้ความสำคัญกับครูผู้สอนฟิสิกส์ในโรงเรียนระดับมัธยมศึกษาให้เข้มแข็งและถ่ายทอดสู่นักเรียนผู้เป็นอนาคตของประเทศที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตบัณฑิตสำเร็จการศึกษาในหลักสูตรวิทยาศาสตร์มหาบัณฑิตจำนวน8คนหลักสูตรประกาศนียบัตรบัณฑิตชั้นสูงจำนวน10คนหลักสูตรปรัชญาดุษฎีบัณฑิตจำนวน5คนผลงานเหล่านี้จะสำเร็จขึ้นมาไม่ได้หากปราศจากผู้สนับสนุนและแหล่งทุนวิจัยอาทิมหาวิทยาลัยนเรศวรสำนักงานกองทุนสนับสนุนการวิจัยสกว.สำนักงานการวิจัยแห่งชาติวช. โครงการปริญญาเอกกาญจนาพิเศษคปก.นิวตันฟันด์ศูนย์ความเป็นเลิศด้านฟิสิกส์เทพสถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนมูลนิธิโทเรเพื่อการส่งเสริมวิทยาศาสตร์ The Abdus Salam International Center for Theoretical Physics ICTP อื่นๆปัจจุบันวิทยาลัยเพื่อการค้นคว้าระดับรากฐานมีคณาจารย์ทั้งหมด 9 ท่าน โดยแบ่งเป็นคณะผู้บริหารวิทยาลัย 4 ท่าน 3 ห้องปฏิบัติการวิจัย ห้องปฏิบัติการวิจัยจักรวาลวิทยาและความโน้มถ่วง ห้องปฏิบัติการวิจัยทฤษฎีสนามควอนตัมและฟิสิกส์พลังงานสูง หน่วยวิจัยฟิสิกส์ดาราศาสตร์และจักรวาลวิทยาเชิงคำนวณ จากอดีตถึงปัจจุบันเรายังคงดำเนินการภายใต้พันธกิจสำคัญอย่างต่อเนื่อง ดังประกาศเจตนารมณ์ท่าโพณวันที่ 8 สิงหาคม พุทธศักราช 2539 เราจะสร้างโรงเรียนฟิสิกส์ที่ดีที่สุดแห่งหนึ่งของประเทศขึ้นที่นี่ โดยหวังเป็นอย่างยิ่งที่จะส่งเสริมสังคมแห่งการเรียนรู้ จุดประกายเยาวชน และสร้างบุคลากรให้มีความเข้าใจลึกซึ้ง เห็นถึงความสำคัญของวิทยาศาสตร์พื้นฐาน ต่อยอดวิทยาการความรู้ด้านต่างๆ ให้ก้าวหน้า บนรากฐานที่มั่นคงทางวิทยาศาสตร์ ซึ่งเป็นกลไกสำคัญให้ประเทศไทยขับเคลื่อนไปอยู่ในระดับแนวหน้าของโลกในอนาคต
All right. Okay. Everyone to the if Colloquium seminar series. This is the 7th in the series. I am Nina Dangniam, the head of, or in Thai, Nina Dangniam, the head of the Quantum Information Science Lab at the Institute of Fundamental Study. This colloquium is also broadcast live as the online viewer may be seeing to promote more public visibility of actually a scientific conversation or communication that happens around in Thailand or in this case the world. This if colloquium is at the, you may notice, at a bit of an unusual time in the morning, at 9 in the morning, because today we have a speaker from Canada, from North America. And okay, so I guess yeah, let me introduce the speaker to you. Dr. Anirban Chowdhury has received a Ph.D. from University of New Mexico in Canada. He worked with Professor Rolando Somma from Los Alamos National Laboratory on topics of quantum algorithms and quantum many-body physics. So actually, we were both University of New Mexico alumni. And then after that, he went on to do postdoc in Canada at University of Sherbrooke, and now he's postdoc in Davis Gosset group at the Institute for Quantum Computing, University of Waterloo, Ontario, Canada. So I believe this is now 10 p.m. for you. So thanks a lot for agreeing to give this talk. And I guess the stage is you have an hour, about an hour, and I guess yeah, if there are questions coming up, or if I have a question, I maybe as we have agreed, maybe we just interrupt you and yeah. Let's see.
Shall I start?
Okay. Yeah. So here give a talk on complexity of approximating quantum many-body physics in thermal equilibrium, right? Okay.
Yeah.
Thank you, Anirban. The stage is yours.
Thank you, Vinod, for the very kind introduction, and thank you for having me give a talk at this colloquium. So today I'll be talking about this work, which is joint work with Sergey Bravi, David Cossett, and Pavel Vokzan. So David Cossett is my postdoc supervisor at IQC. Sergey and Pavel are scientists at IBM. And in this work, we are looking at basically what is the computational complexity of basically doing quantum physics. Suppose I have a many-body system, a quantum many-body system, and I want to compute its properties when it's interacting with some thermal path. Well, under what conditions is this problem tractable? Under what conditions can I have efficient algorithms? And under what conditions is this completely ruled out? That's the kind of question we are trying to understand in this work. And we made some attempts at looking into this. So this talk will be broadly about two different topics that were in this paper. The first is some work on understanding something called the computational complexity of approximating partition functions of quantum systems. Okay. And the second part will be an efficient classical algorithm for approximating the log partition function of the free energy of certain quantum Hamiltonians. So there'll be somewhat like two disparate topics, but they're broadly aimed at understanding basically the computational difficulty of these kind of thermodynamic problems. So in the first part, I'll go over roughly these three things, and this will be more of like a high-level overview talk where I'll just mostly talk about the results and sort of the rough intuition as to why how they come about. In the second part, I'll go into a little bit more detail. I'll talk about the algorithm, which is basically something like a variational algorithm for doing this kind of problem. But it will be a unique twist on it, where if you won't do like a variational algorithm assuming some kind of ansatz, we'll introduce some ideas from something called convex relaxations or semi-definite programming relaxations. And there'll be lots of interesting things that you might find quite interesting. So with that, let's go on to the first part of the talk. And for that, I'll try to first introduce some basic ideas in computational complexity theory. So here we are trying to essentially classify computational problems based on how difficult they are. And the first kind of simplest kind of objects you think about are what are called decision problems. Here you have some kind of computational problems. So someone hands you say some bit string and asks you to solve a particular problem on it. And at the end, the answer should be something a yes or no. It's a one-bit answer. So these are called decision problems. You just decide whether it's a yes or a no. And computational complexity tries to understand, given these kind of problems, let's say decision problems for now, over some bit strings of certain size n, how much resource does it take to solve a problem? And in resource, you can think of both the time complexity or the space complexity, which is how much time do you need and how much space or memory do you need. And here, for the purpose of this talk, we'll mostly think about the time complexity, how much time do you need. And here, people call something an efficient algorithm if the problem can be solved in time that goes roughly as polynomial in n. If it were to go as, say, an exponential, then this would be an inefficient algorithm. So that's like the second thing we should keep in mind. The third thing that will be useful to us is something called a reduction. So a problem, let's say there are two different problems, A and B, both are decision problems. And we'll think of them as having roughly the same complexity, which would mean that if I can solve A efficiently, then by solving A a polynomial number of times, I can get an answer to B. So this means that having the ability to solve A gives me the ability to solve B in polynomial time. So that means that these two problems are equivalent under like something called polynomial time reductions. So this also proves to be a useful idea in these kind of computational complexity classifications. So basically, all problems that are reduced to each other in polytime sort of have the same complexity. That's the idea that computational complexity classifications try to capture. And for that, people define various computational complexity classes. So the first class, which some of you might be familiar with, is something called P. This basically means the class of problems, or decision problems to be more precise, which you can solve in polynomial time, given some kind of classical digital computer. All right. So that's P, everything you can solve in polynomial time or efficient. Then if you have NP, which is a larger complexity class. So NP does not stand for not polynomial. It stands for something called non-deterministic polynomial, but the name isn't important. The key idea is that in NP, you can verify solution in polynomial time. So think of something like factoring. You're given like, let's say, some composite number, and you want to find its prime factors. We don't know efficient algorithms for finding this, but if someone hands you two numbers and says that these are the prime factors, well, you can multiply those numbers together in polynomial time and verify that they actually multiply to the right number. So that's an instance where the verification is easy, but actually finding the solutions might not be easy. So that's an instance of an NP problem, okay? Problems whose solutions you can verify in polynomial time. So these are classical complexity classes. And another classical complexity class that is useful to us is often something called BPP. And you can think of it as roughly as the probabilistic analog of P, which means that you get the right answer with some probability greater than half and the wrong answer with probability less than half. But we won't think too much about that. The key part that we want to think about is something called BQP, which is the Q here stands for quantum. So this means that if you're given some kind of quantum computer running, say, having a bunch of qubits, running some quantum operations on it, quantum gates on it, then the class of problems which you can solve with probability at least half, you get the correct answer with probability at least half, all that stuff, that is called BQP. So everything that you can do with a quantum computer that contains all the problems that you can solve efficiently on a classical computer. So BQP contains P, but the curious part is also that it somewhat, at least we believe that it kind of sticks outside NP as well. So this is like BQP is everything we can solve efficiently on a quantum computer. Then we also have the quantum analog of NP, which is called QMA. This you can think of as problems whose solutions you can verify in polynomial time on a quantum computer. So a prototypical example of this is basically the problem of finding the ground state energy of some kind of Hamiltonian. So if someone gives you a Hamiltonian and asks you to find its ground state energy, that's a very hard problem, and you cannot do it in polynomial time. But if someone hands you a quantum state, or so-called witness, then you can run some quantum algorithm on it and verify that its ground state energies, that the energy corresponding to that state is small enough. So that means that this is a problem you can sort of verify in polynomial time, having access to a quantum computer, but you cannot necessarily solve. So these are like sort of rough complexity classes we'll encounter, at least in the first half of this talk. But the main point, the key ideas to keep in mind is that quantum is a bit more powerful, and that being able to verify something does not necessarily give you the ability to solve something. So there are these two distinctions. So with these elementary complexity ideas out of the way, we also get to two other concepts. The first is that a certain problem is said to be hard for a complexity class C if all other problems in that class reduce to it. So if you can solve that problem, everything else you can solve by just solving that problem a polynomial number of times. That's what it means to be something to be hard for a complexity class. And then you also have the notion of a complete problem. So if in addition to being hard for a certain complexity class, you can solve that problem in that complexity class, then that problem is said to be complete for that complexity class. Okay, so it's both contained in C, and every other problem in C is equivalent to solving that particular problem. So these notions of hard and complete will also be useful. So now, with that out of the way, we'll now get to thermodynamic problems. So here, you'll think about these two quantities. We're given some Hamiltonian H, okay? It could be classical, could be quantum. And its partition function, Z, is given by the trace of exponential minus beta H. So beta here is at something called the inverse temperature. It's 1 over kBT, where kB is the Maxwell-Boltzmann constant. And we'll think about computing this quantity and also its log, the Helmholtz free energy. So why we want to compute these? Because these are very important thermodynamic quantities. If we can compute the free energy at various different temperatures or various different values of like your parameters in the problem, you can map out the phase diagram of many body systems and figure out its properties. This is really why we want to compute these properties, compute these quantities in physics. In physics, we look at data in a lab, we come up with some Hamiltonian, but we might not be able to necessarily figure out everything you want to know about it, given that Hamiltonian, because computing these things might be difficult. So that's what we're trying to address in this talk. So the question that we are asking is that, how difficult is it to compute these physical properties, such as the partition function and free energy, for quantum systems in thermal equilibrium? So I told you about these complexity theoretic classifications. So to these particular problems, this free energy and partition function, computing these, fit into some natural complexity classes. That's the thing we want to go for. And our motivation is that for solving ground state problems, answering whether how difficult it is to compute the ground state energy of some certain local Hamiltonians within some specific error guarantee, this is hard for the complexity class QMA. So QMA, you recall, is a set of problems you can verify efficiently on a quantum computer, but not necessarily find efficiently. So we have a nice characterization of these kind of ground state energy problems. But the issue is that for thermodynamic quantities like the partition function, this kind of classification is somewhat unknown. So that's what that's what motivates us to tackling this problem. So I talked about this partition function. Now it turns out that even for like classical spin systems, computing this partition function exactly is very hard. So here we're looking at something like just an Ising model. So these xi, xj's are spin state going like up or down, and therefore taking plus minus 1 values. And this is like the energy function. And its partition function looks something like this. So it turns out that this partition function can encode solutions to some very hard graph theoretic problems, such as computing some perfect matchings of a bipartite graph. And this is, it's a very difficult problem. It's something called sharp P complete. So this sharp P is not a class I introduced before, but it is the main thing you should want to know about this. It is a class that's much larger than NP or even QMA. Okay. So firstly, it is defined in terms of something called counting problems. So NP, recall, are a set of problems which have like yes or no answers, and we can verify whether something is a yes answer efficiently. So now, if given some kind of NP problem, we now ask the question, well, how many yes solutions those are? That precisely defines something, this sharp P problem. Okay, so as we can have complete problems for NP, we can also have sharp P complete problems, which sort of capture the difficulty of this computation complexity class. And it turns out that computing the partition function is complete for this class, and it's like a ridiculously large class, and we have no hopes of solving, therefore, the partition function exactly. Now, it turns out that approximating this is slightly easier, actually a lot easier. So here we're thinking of something called a multiplicative approximation. So Z here is the true partition function, and we want an estimate Z hat that is within some 1 plus epsilon factor of the true value. So epsilon here is a small number. So it turns out that due to some fundamental complexity theoretic results, something called Stockmeyer approximate counting, we can get multiplicative approximations to the partition function if we have a BPP machine. So a BPP machine means that it's a classical computer with access to some random bits. So it's a probabilistic classical computer, which lets you solve problems with some bounded probability. So if you have a BPP machine with the ability to make oracle queries, or so just queries to some kind of NP machine, which can just tell you yes or no answers to NP problems. If you have a machine like this, which sort of sounds convoluted, but the main point is if you have a machine like this, you can solve this kind of, you can count the number of witnesses accepted by an NP machine approximately, and therefore you can approximate the partition function within this kind of error guarantee. So why this is interesting, despite this being maybe perhaps a little bit convoluted, is that this BPP with an NP oracle is somewhat closer to NP than full sharp P. Okay, so sharp P, so P raised to sharp P is sort of like the decision variant of sharp P, but we won't worry about that. For all purposes, you can think of it as being equivalent to this large class sharp P. So the point here is that this BPP raised to NP is closer to NP than to sharp P. So it's like we have a characterization of it, and we know that it's less difficult than this huge complexity class. Now, we also have a bonus fact that the ground state energy problem for these kind of Ising models is in fact NP complete. So this gives us a nice characterization of this of classical spin systems. We know that the ground energy problem is NP complete, and that the approximating thermodynamic quantities, it falls in this BPP raised to NP, which is in something called the third level of the polynomial hierarchy. This is a smaller complexity class than this P raised to sharp P. That's the main point. Now, the issue is that was all about classical partition functions. If we now go to quantum partition functions, this kind of classification for the approximation problem is lacking. We know that exact computation is as hard as other sharp P problems. But if you ask for this multiplicative approximations, we don't have this kind of nice characterization. We know it's as hard as recovering the ground state energy with an additive error. So QMA hard. And we can solve in this huge complexity class, which is P equipped with some kind of sharp P oracle. But because we don't have a quantum analog of approximate counting, which we could do for the classical setting, this kind of, we don't have a classification of this approximation problem for the quantum partition function within a class that is, say, easier than this P raised to sharp P. And the part of the problem here is kind of defining what you mean by approximate counting. So for NP, your solutions basically are like, or your witnesses to yes or no problems, those are just bit strings. Your variables can only take 0, 1 values, and therefore you have like 2 raised to n bit strings, let's say. In quantum problems, your witnesses or solutions are like quantum states, which are in some sense continuous because they can have complex amplitudes. So part of the problem here is kind of defining what do you mean by counting here and what is approximate counting. And that's kind of what we address. So some caveats here is that we are thinking of multiplicative approximation for this real temperature. For other things, the problem becomes slightly more different, but I won't talk about that much. Now, more precisely, here we have this QPF problem. So we are given some K local Hamiltonian. So K local here means that this is local in something like the computer scientist sense. So K local means that the Hamiltonian consists of K body terms. So K body would be the more physics appropriate term. So each term in the Hamiltonian acts on at most K qubits at one time. And you have a sum of these in the Hamiltonian. And our goal is to find a multiplicative approximation to the partition function. And we want to know, is there a computational complexity class? Can we define a computational complexity class, which is not this ridiculously large sharp P, for which the QPF is a complete problem, okay? Which means that we can solve the QPF problem in that complexity class, and all other problems in that complexity class reduce to solving the QPF. That's what we want to answer. Unfortunately, within the scope of our paper, we don't answer that question. But what we do show is that we can define certain other quantum problems that capture the idea of approximate counting in the quantum setting, such that if we can solve those problems, we can solve the QPF. And if we can solve the QPF, we can also solve those problems. So these problems are basically equivalent. And the hope from that is that we can now use these other approximate counting problems to define a nice computational complexity class. So that's like kind of the rough framework for this work, the context for this work. Now, our first problem that we define is something we call quantum approximate counting. So here we have something called a QMA verifier circuit. Okay, so here we have some input quantum state psi, we run some polynomial size quantum computation on it with some poly n qubits, some gates, etc. And we do a measurement on one qubit at the end. And a problem is said to be in QMA if this measurement returns to us 1 for all psi, such that the answer to some problem would have been yes, and it would return no for all psi, such that the answer were no. And here we have certain probabilities. So for yes instances, this bit would flip to 1 with probability at least A. And for no instances, this bit would flip to 1 with low probability B. Okay. So yes means you get 1 often, and no means you get 1 infrequently. And there's some 1 over poly n gap between A minus B. Typically, you can take like A to be 2/3 and B to be 1/3, but this gap is like a promise. So this defines QMA. And what we want to do is now we want to define some kind of counting version of it, where we want to count how many states psi are accepted, how many states psi fall into this yes category. So we do this by noticing that this quantum circuit followed by a measurement implements something called a generalized measurement, or a POVM, with 2 elements, A and I minus A. And the probability of getting 1 is given by the inner product of this A, this bracket psi A psi. Okay. So now we can now count something like the dimension of the subspace spanned by eigenvectors of A with eigenvalue greater than or equal to lambda. So all eigenvalues of, so let's say if you were to feed in NA over here, you would get the dimension of the space for which this bit flips to A. Now you can fit in like NB over here, and you would get it's like something like this part of the argument. So we define this approximate counting as follows. So given this kind of verifier circuit and some target error, our goal is to output an estimate n hat satisfying these 2 bounds. So it lies between 1 minus A times NA and 1 plus A times NB. Okay. So this is what we're estimating. And we have these 2 different things, NA and NB here, because we might have the case that this psi, this state psi, doesn't fall into these either categories, whether it flips with probability A or doesn't flip with probability B. So that's why we are allowed to miscount those states with some small error. That's what these 2 different things on the side are telling you. Now, do you have a question?
Yeah, actually, I wonder the whole time whether this, is there any relation to this to something like gap P problem in like quantum supremacy, where you, you look at, the problem is, I think, approximating the probability of, say, the first qubit having outcome 1.
Right.
In a random circuit or something.
I mean, I guess if you want, like, so if you are asking for estimating the probability within some multiplicative error, that is probably like post PQP, and therefore that will be pretty hard. But that's like, I think that would be equivalent to, that would be like a Sharpie hard. It'll be pretty close to Sharpie hard, I think.
I see. Yeah. So I think this QAC is something in between that and, I guess, so, the hardness of sampling in quantum supremacy, because in those cases you so what in the quantum supremacy like argument, what we want to rule out is something much easier than like approximate counting to exponential precision, right? Because in the end you want like a total budget of additive error of all the outcomes or something.
Right. So like so in certain cases, even like approximating the partition function with like a complex temperature, that we know is Sharpie hard for some range, the complex temperature. So you can also interpret that as, I think, approximating the like the output probability of some quantum circuit with a multiplicative error, that is also Sharpie hard. Okay, because like complex temperature partition functions, you can map to like output probabilities. So here we're interested in like the real temperature version, which is why we're defining this QAC. And the hope is precisely as you said, that it would lie like somewhere in between between like this p raised to sharp p and QMA. So that's like the idea.
Okay. Yeah. Thanks.
Yeah. So right. So here basically what we are saying is like NA would be the probability of getting 1 here. So that's why we are estimating this 1 minus A times N, or getting estimated N hat between these two limits. So this is like the definition of QAC. And with that, that brings to the first result of our paper. We show that if you have an oracle that solves this quantum partition function problem for two local Hamiltonians, this can also solve this quantum approximate counting problem. And the proof idea uses some techniques, something called the circuit to Hamiltonian construction. So this was something introduced by Kitaev. And the idea is you take a quantum circuit and map it to a Hamiltonian such that all the states psi, which are accepted by the circuit, they correspond to eigenstates of the Hamiltonian with energy close to 0. And all the states that are not accepted, plus all other states that come into the, like, you have to enlarge the Hilbert space, so you introduce some additional states. So all those additional states, plus all the states that are not accepted by this circuit, they get some kind of energy penalty. So then if you compute the partition function of this Hamiltonian, most of the contribution will come from these zero energy states, which correspond to the states that are accepted. And therefore, you've sort of, by approximating this partition function, you've approximated the number of states that are accepted. That's like the loose argument. So that's the first reduction. The second is we define something called another approximate counting problem, which is, suppose you're given a local Hamiltonian with some range of eigenvalues. You pick out some small range on it, small interval in that range, and ask how many eigenvalues lie within that interval. This is like the density of states problem, which is encountered often in many body physics. So we show that the ability to solve this quantum approximate counting also gives you the ability to solve this k-local q, this quantum density of states problem. And this is basically because this kind of lets you count like the eigenvalues of a Hamiltonian close to its ground state energy, and also like in any other energy bin. So this is like a fairly straightforward reduction. Then we show that if you can solve this k-local quantum density of states problem, what you can do is basically take your Hamiltonian, split your possible range of eigenvalues into small bins, enumerate the number of eigenvalues in each bin, then weigh all of that by this your Maxwell-Boltzmann factor, and essentially reconstruct the partition function of the same Hamiltonian. So you're binning your eigenvalue range, and figuring out number of eigenvalues in each bin, assigning to it something like the midpoint of that range, and then using that as a proxy to reconstruct your partition function. So that shows you that basically all these problems are equivalent. So here you can take k equals to 2, and you would show that that basically if solving q DOS, this density of states is also equivalent to solving the two local QPF problem. And the last part, which is somewhat different from all these reductions, is that we show that the ability to estimate expectation values of, say, local observables, so few qubit observables, in the thermal state or the Gibbs state of a quantum Hamiltonian within some additive error, also gives you the ability to compute the partition function. And also, computing the partition function enables you to estimate thermal expectation values. So from k-local QPF to k-local QMV, that's somewhat straightforward. You can think of, well, being able to compute expectation values of observables by taking derivatives of the partition function, something you might have encountered in statistical physics. And the same idea essentially goes through, we can write down a derivative, make some finite difference approximation to it, and then express approximating the quantum mean value of some local observables as a difference of two partition functions. And then by choosing our parameters appropriately, our errors carefully, we can show that the ability to solve the partition function also gives you the ability to solve this k-local QMV problem. So that's like the full chain of reductions. And we show that, therefore, that the QPF is equivalent to all these three problems. Now, the hope is that someone will take now one of these definitions and then address the question, well, what is the complexity of the quantum partition function? So maybe someone can define a complexity class which will capture the difficulty of solving these problems. So that kind of brings me to the end of the first half of my talk, which was about like a rough idea of the complexity theoretic issue in these thermodynamic problems, the question we are trying to address, and the progress we have made towards it. So in the next half of the talk, I'll try to talk a little bit about a different topic, which is an efficient algorithm. And the motivation is that, well, even though we don't know precisely how hard approximating this partition function is, we know that for general k-local Hamiltonians, it's still pretty hard. It's QMA hard, and QMA is a large complexity class. We don't expect to solve QMA hard problems given even quantum computers. But we know that in special cases, so something like special local Hamiltonians, there are efficient approximation algorithms for these partition functions, even efficient classical approximation algorithms. And in our work, we give an efficient algorithm for a new class of something called dense local Hamiltonians. And here, we're slightly changing the problem. We will think of approximating something called the free energy, which is the log of the partition function. So this is the Helmholtz free energy. And we'll think of the following scenario. We'll think of just two local interactions. So let's say ij here label qubits going from 1 to n, and we have terms in the Hamiltonian that act on only 2 qubits at a time. Okay, so it's like hij tensor identity on everything else. So this could be something like a Heisenberg model, something like that. Now our goal will be to estimate the free energy within some kind of relative error. So we'll get an estimate f star, which is within some fraction epsilon of the maximum possible energy. So this here indicates the norm of this individual interaction terms. So you sum the norms of all of these terms and ask for an error that is epsilon times that. So this is a different, so one way to see this is that if each of these hij's has norm at most 1 over n, and we would demand that this be 1 over n if we want like the energy per qubit to go be a constant. So if we have this kind of normalization, we'll get an f star that is within epsilon n of the true free energy. So it's like an extensive, the error itself is extensive in the system size. So this, and we'll also assume that we'll do this calculation for something called a dense interaction graph. So these orange dots here now represent qubits. So this is a graph. The vertices are qubits, and the edges represent between which pair of vertices, which pair of qubits there are interaction terms. Each edge represents their existing interaction term. So this is a complete graph indicating that all the qubits are coupled to all the other qubits by interaction terms. Now, if I remove a small fraction of these edges, this will be a dense graph. So dense graph just means that you have a complete graph over some n vertices, and you remove a small fraction of the edges. So that's why I say it's almost all-to-all coupling. So this is the kind of model that we'll think about for the rest of the talk. And we'll ask, can we approximate the free energy for these problems? A bit of context as to why we think this is important. Well, there's something called the quantum TCP conjecture, which says that even for the kind of error guarantee we talked about, getting the approximation within that for the ground state energy is also QMA hard. So it's a hard problem. And free energy you can think of as being a generalization of the free energy, where so if you take beta to be beta going to infinity, the zero temperature limit, that basically recovers the ground state energy. So the free energy problem is a generalization. So we expect that it is also as hard for general local Hamiltonians to get this kind of error guarantee. But for the specific case of dense 2 local Hamiltonians, people have shown that you can estimate the ground state energy using efficient classical approximation algorithms. These are some seminal results by Karipian and Kempe, Brandau and Harrow. Now, this is only for the ground state energy, and our work is sort of generalizing these results to the case of thermodynamic problems, which is for this free energy problem. And we use somewhat different techniques or different ways of doing things than is done in this paper. And our result, which I'll just quickly flash here, is that we get an algorithm which the scaling is n raised to roughly 1 over epsilon squared. So if we demand that this epsilon here is a constant, so a constant relative error approximation, this is a polynomial time algorithm. Now, the issue is that if we want epsilon to be 1 over poly n, this thing blows up. And that basically means that having this algorithm doesn't give us like a multiplicative approximation to the partition function, which we were asking for in the first half of the talk. So this is the problem we are solving here is in some sense an easier problem. So now I'll talk a little bit about how our algorithm works. So our algorithm is based on the variational characterization of the free energy, which some of you might be familiar with. So if I take this functional, so this is the free energy functional in the brackets. So it's a sum of trace of rho h. So this is the average energy term and an entropy term. So S of rho here is something called the von Neumann entropy. It's trace of rho log rho. If you minimize this trace, this free energy functional over all possible rho, over all possible density matrices rho, I will recover the true free energy. Now, the problem is that I cannot do this minimization efficiently because this rho for n qubits is an exponential sized matrix, and therefore I cannot even write one of them down in polynomial time. So that doesn't work. So we need to do something else. And optimization is too difficult. So what we do is we relax and we solve something called a relaxed problem, an easier optimization problem. And this relaxation is defined by just looking at reduced density matrices. Okay, so think of just the average energy term in your in the free energy function. That was like this trace of rho h, and your h is too local, so it has just two body terms. So here, what I'm doing is I'm storing marginals on some few qubits. Let's say k equals 3 here. So I'll store all possible reduced density matrices or marginals on all possible subsets of 3 qubits, something like this, but also something like this. Okay, choose all possible subsets of 3 qubits and keep marginals over them. And the other thing that will demand is that these marginals must be consistent locally. So if I retain a marginal on this qubit and I retain a marginal on this qubit, okay, a reduced density matrix on this 3 qubits, these 3 qubits, well, they'll both define some reduced single qubit density matrix on this place where they overlap. So the point is, whatever thing you get in this one qubit by tracing out, let's say this part, that must be consistent from what you get by tracing out this and this from the other marginal. That's what it means to be locally consistent. So if you look at if you examine only 3 qubits at a time, everything should look like you had a valid density matrix. But the problem is that, or the cool part is that, if I now ask, well, what quantum state does this define on this larger set of 6 qubits? Well, there won't be any quantum state defined, or there won't be any valid quantum state defined. You might define a matrix, but it won't be, let's say, positive semi-definite. So the key idea is that you're computing some objective function just from these local density matrices, but you're relaxing that these reduced density matrices come from some global quantum state. So global consistency of marginals is relaxed. And why you're doing this is that if I can store all k local marginals as an object of size that goes as this. So it's 2 raised to 2k times n choose k. And this is much smaller than 2 raised to 2n. Okay, that's really the main part. I'm making my data structure smaller. So in terms of this reduced marginals, I can define an easier optimization problem, which I just stored these reduced density matrices, and I'm going to calculate a relaxed objective function only from the marginals. Okay, and this is slightly non-trivial because for the average energy part, which was just trace of rho h, that kind of follows straightforwardly. I can compute some value of it if I just have marginals, even though they might not be globally consistent. But for the entropy part, it'll be somewhat non-trivial. So that's why this is a separate bullet point. Now, the problem is I'm going to now minimize this relaxed objective. I'm going to solve this relaxed optimization problem. But what I'll get is a possibly inconsistent set of reduced density matrices. Okay, so this won't correspond to a valid quantum state. So the value of the objective that I've got might not correspond to anything realistic. So I would have got some value, but it might not correspond to a true free energy. So to deal with that problem, what we do is we look at these inconsistent reduced density matrices and do some operation on them to patch them up into a global quantum state. And this is something called a rounding map. And in this case, what we are doing is we are basically building upon some results by Risteski for the classicalizing model, and you are doing that in the quantum setting. So this is the overall idea of our relax and round scheme. And just to motivate as to why this idea is useful is that relaxing minimization problems to a larger set of objects can make things easier. For instance, integer programming, which is like minimizing some functions over integers, subject to some linear constraints, is NP hard, but its relaxation. So if I just let these xi's here be like real numbers instead of integers, that you can solve in polynomial time. But again, as I mentioned in the previous slide, this takes you out of the feasible set of objects. Instead of integers, once you do the minimization, you get real numbers. And instead of a true minimum, you get a lower bound. And therefore, you need to round these real numbers to integers, which kind of explains this rounding terminology. But this is the idea that going to a larger set of objects, going from consistent marginals to inconsistent marginals, can make your life easier. So in terms of, just to give you a better, like a more idea of the schematic, we are finding this relaxed optimization problem. And the way we set up this problem is that we ensure that this relaxed objective f tilde, we're computing from these set of marginals rho tilde, it kind of lower bounds the true objective, which is that if I evaluate f on some density matrix and I evaluate f tilde on some density matrix, I'll always be assured that f tilde is a lower bound on f. And I'll also ensure that this f tilde is convex. So it follows that now if I minimize over, if I solve this relaxed optimization problem, I get some f star, which is a lower bound to f. Now the issue is, now the problem here is that I don't know how bad of a lower bound is. I don't know how much this gap is. And to mitigate this, I do this rounding, which I take this rho tilde min, and I patch them up into some global quantum state, which I alluded to before. And the cool part is that this rounding is arranged such that the difference between this f star and f0 is bounded. So I'll know that f star minus f0 is less than or equal to some epsilon. So even though I do not know at the relaxation stage how far my f and f star are, I know at that f must lie below f0 because f is like the minimum of this objective over all possible quantum states, and rho 0 is the valid quantum state. Therefore, f0 must lie above f. And I know that f star is below f. And therefore, by bounding the difference between f star and f0, I have also bounded the difference between f and f star. This is the whole idea of this relax and round strategy. So that is what we do in our algorithm. Now, as I mentioned, you need to think a bit about what to do with the entropy term, because for the Hamiltonian, the h is too local, and therefore you can compute trace of rho tilde h, some functional version of that if you just have local marginals. But the entropy, it's like trace of rho log rho, and you can't just kind of compute it just having the marginals. So what you do is we define something called a pseudo entropy functional, which is something like a mean field entropy, but with some twists. So here what we're doing is we are choosing some small subset C of size at most k minus 1, keeping the entropy of computing the entropy of that subset according to whatever marginal is defined on that. And we recall that we have marginals on systems of size, subset of size at most k. So we can do that. And then we have a sum of conditional entropies, with the conditioning being on the subset C. So the conditional entropy is defined in the following form. So conditional entropy of B given C is defined as the joint entropy of B and C minus the entropy of C. So here the set C being of size at most k minus 1 comes into play. This means that the set of B union C has size at most k, and therefore I can compute these conditional entropies from having these local marginals. Okay, so that's really the main part. And what you can show is that this entropy, this pseudo entropy functional, bounds the true entropy in the right way, and it's a concave function of the marginals, which means that if I just substitute it into my free energy functional, I'll get an f tilde objective, a relaxed objective, which will be convex, and therefore I can run convex programming on it. And this will also lower bound the true free energy function. Okay, so that kind of deals with the relaxation step. What is left is now to argue what to do with this rounding map. Now, for the rounding map, I need to do a little bit of context switch and ask you to think about just having probability distributions, okay, over like some kind of classical spins. So everything that I said before will also equally hold true if I just have like classical spins taking plus minus 1 values, something like an Ising model. I can think of computing the free energy of the Ising model. And instead of having like locally consistent reduced density matrices, I can think of having locally reduced, locally consistent marginal probability distributions. over at most k spins. So that's the thing I'll ask you to think about. And then our goal will be to round from these locally consistent marginal distributions to something like a global distribution. And our goal will be to do this in such a form. So once we do the minimization, we'll get some p tilde, and we'll round it to some p such that this value of this 2-point correlation function, xi, xj, this will be, the change in that will be small. So this fancy e here denotes, the subscript p denotes which thing you're taking the expectation with respect to. And both p and p tilde will define distributions on these like sets of 2 variables. So therefore, I can compute these expectations. And what we're trying to say is that the average value of xi, xj should not change by much due to this rounding. That's what we're trying to ensure. And to do this, what we'll actually ensure is that if we look at the marginal on these two, on let's say the ij system, ij subsystem, coming from p, and take its difference on the marginal on the same system, but now coming from the pseudo distribution p tilde, that should be small. Okay, so that's what we are trying to ensure over here, that the difference between these two marginals, how much they change, on average, if you take the average over all possible edges, that should be somewhat small. And how we do this is as follows. So our relaxed optimization gave us a collection of k local marginals, which may not be consistent with a global distribution. Okay, so you have marginals on, let's say, these overlapping subsets. And the goal is to patch them up. And the way to do it is as follows. Okay, we choose a set C of size at most k minus 1, sample some assignment to the spins in it, some xc, something like, so xc basically denotes which spins are plus, which spins are down, or plus or which spins are minus 1, etc. So we sample some assignment on it xc according to the local distribution. Once we have done that, we look at all the other spins that are not in the subset C, and we sample them conditionally. So we sample some value x1, conditioned on the fact that we got xc in the subset C. And if we keep repeating this conditional sampling with condition on this, whatever outcome xc we got here on all the other spins. And why we're doing this is because recall that we have valid distributions defined on everything up to size k. So we can sample this xc, and we can also sample this x1 given xc if you have access to these k local marginals. That's really that's the idea here. So doing this allows us to patch up these possibly inconsistent marginals into a consistent global distribution, which looks like this. So it's like a product of some distribution over this xc's. Then we have a product of conditional distributions conditioned on whatever xc you got here. Okay, so the point is that all the spins j that are not in xc, they're kind of mutually independent once you have conditioned on this small subset C. And the intuition is that you can formally show that this is true, that conditioning on a small subset of variables makes the others almost independent. And how you do that is by computing something called the mutual information between two spins I and j that are not in C, and showing that the conditional mutual information is kind of small if you take the average. And once you've done that, you can show that how much your local marginals, like whatever distribution p tilde defines on ij, and also what p, the rounded distribution, defines on ij, the rounding error, the difference in these two local marginals, it will go down as 1 over square root of k. So k here is the maximum size of the subset up to which you're keeping like these local marginal distributions. So this is the idea of something called correlation rounding, which we take from the classical optimization algorithms literature, or like these these ideas of semi-definite programming hierarchies. So this is all for the classical setting. So I will skip the next 2 slides, maybe, in the interest of time. Now our goal will be to now make this quantum. And the problem here is that, well, I talked about this, doing this conditioning on, like doing a sampling on some small subset and doing a conditioning. In the quantum case, this becomes a lot more difficult. So in the quantum case, you might say, okay, I can just measure things in some kind of orthonormal basis and look at the outcomes condition on that. Turns out that does not work. This defining a conditional density matrix is fairly tricky. And there's some ways to see it. One way that kind of illustrates it is that For a classical distribution P, if I write down the conditional Shannon entropy, so something like HA given C with respect to some distribution P, I can write it as a sum of all the possible outcomes in this set C. So XC taking values XC. So it's a sum of conditional entropies, with the conditioning being on a particular outcome. Now, in the quantum case, if I let this XC be outcomes of measurements in some orthonormal basis, this kind of relation does not hold. And therefore, I cannot really define a conditional density matrix, which will correspond to the nice bound on the mutual information I had in the earlier slide. That's kind of the issue over here. And the main problem, of course, is that just having projective measurements in one particular basis does not capture the fact that in quantum mechanics, you can have superpositions or coherence more generally. So what we do instead is, borrowing some ideas from other papers, is that instead you do an informationally complete measurement. So this corresponds to basically doing a measurement in all possible bases. So for a qubit, you choose like one of Pauli X, Pauli Y, Pauli Z at random, and do a projective measurement in its eigenbasis. And if you have the measurement outcomes in corresponding to up to or like plus minus values in all three of these bases, you can recover the full density matrix. So knowing the probability of each of these 6 outcomes completely specifies the full density matrix of a single qubit. So this is why it's called an informationally complete set of measurements. Having these probabilities is equivalent to having the quantum state. So this ICP-OVM, it takes a density matrix rho and converts it to a probability distribution containing the same information. So what our quantum rounding scheme looks like, by borrowing some ideas from Brandau and Harrow, is that we use this informationally complete POVM to convert pseudo-density matrix, or this set of local marginal density matrices, to informationally complete set like local marginal probability distributions, P tilde. Then we do our correlation rounding, condition on a small subset, make everything else uncorrelated, that idea, in the space of these pseudo distributions, and we round to some valid distribution P0. So we had some inconsistent marginals, we round them to some valid distribution. Then we apply the inverse of the POVM map to convert P0 to a valid density matrix, rho 0. So doing this, we can show that the 2 local marginals of this rounded density matrix, once you go through this full convoluted scheme, are close to the 2 local marginals of P tilde, the set of inconsistent marginals that you had. And then you show that at least in terms of the energy, you have not lost much in your objective. The problem that arises is that you need to think a little bit about the entropy, but I won't. I probably won't talk about that. So maybe in the interest of time, let me just skip to the final slide, or like the later slides. So to do the entropy part, what we need to show is that this density matrix that you get after rounding, if you compute the entropy of that, that has to be greater than the pseudo entropy functional, this thing with the conditioning that we had earlier of the pseudo density matrix, or your set of inconsistent marginals. And this is really the main, like one of the main technical parts in making our algorithm, or making the proof of our algorithm work. So the classical analog, with when you just have probability distributions, it's fairly easy. But here, because we have this like informationally complete POVM, the conditioning on the outcomes of that it becomes a lot trickier. So quantum conditioning is difficult, as Boromir is telling us over here. And one thing I mentioned is that we can make our proof work only for this random Pauli POVM that I mentioned a couple of slides back. So other technical details that we also prove in the paper is that we need to show that when we are doing this conversion between density matrices and distributions, if 2 distributions are like differ by a small error, that difference shouldn't blow up in this conversion. So for that, we need to bound something called the distortion of this informationally complete POVM. And the final part is, well, I talked about, well, we are defining some kind of convex optimization, but we need to make sure that this convex optimization, there's actually an algorithm for it, that it maps to some known theorems about convex programming. So we also make this work in the paper by appealing to some known results and formulating the problem in a way such that we can appeal to those results. So given that, our relaxation rounding scheme goes through, and we get an algorithm with this kind of performance, I have this delta parameter here, but in the interest of time, you can ignore it. So the algorithm just goes as this 1 over epsilon square. And the nice thing is that it has some kind of different conversion criteria than other algorithms people use to solve these kind of free energy problems, such as Markov chain Monte Carlo or using polynomial approximation. And though we didn't prove it in the paper, you can extend these techniques even to qubits and Hamiltonians on graphs that are somewhat more general than dense graphs. And finally, for a bit more context, so one thing I did not stress is that the algorithm itself, it's just the relaxation part. So you just run this relaxed optimization program and you're done. The rounding part, which was this more complicated, involving like all these POVM ideas and this correlation rounding, that is just to show that the free energy that you get, it's actually close. So that's only for the provable guarantee. If you just want to run the algorithm, it's kind of conceptually quite simple. And if you ignore like the entropy part in the free energy problem, if you just minimize the average energy, this algorithm will basically find the ground state energy or an approximation to it. This is slightly different from these other papers, which also solve this ground state energy problem for dense Hamiltonians, where they show that first that you minimize over some ansatz of like product states, okay, which are like classically tractable. But first you need to show that such a product state exists, which can approximate the ground state energy to good approximation. And then you need to run some kind of optimization over the set of product states. And that optimization can be somewhat trickier. So in this sense, I would say that our algorithm is some ways conceptually perhaps simpler, perhaps. And just to give you for a bit more context, there are lots of recent work that also explore these kind of SDP relaxation ideas for this ground state energy problems for quantum Hamiltonians. To just give you a quick summary of our results, our paper has a bunch of different things. I briefly talked about the first part and the second part in this list. We also have some results on improvements to other exponential time algorithms. I won't mention them here, but there's a link to a talk that I gave recently that covers some of these. Now, for some open questions, well, for the first part, we also, of course, want to know what is the complexity of this QPF problem. But it might be, as smaller steps, it might be interesting to ask, are there other interesting problems which are equivalent to solving the QPF, other than the ones we have found here? And in a bit more detail, are there better notions of approximate counting for quantum problems? For the efficient algorithm part, there are some other questions that I would like to know is that, well, for one, the algorithm that we have is tailored for these complete or dense graphs. And an interesting thing to ask might be, for other interaction graphs, are there other sensible rounding schemes that work and give you some kind of approximation? And the key thing to keep in mind is that at the end, all we're trying to show is that there exists a quantum state with approximately the same marginals. So maybe just keeping that in mind gives you some idea as to how you can generalize this result to other settings. So with that, I'll thank my collaborators and our funding agency. And thank you all for listening.
Yeah, thank you, Anirban. Yeah, that was an excellent talk.
Thanks.
Yes, I don't see a question in the comments, so maybe I should ask my own question. But just to make sure, so for the routing map, eventually you use the patching algorithm. You use the classical patching algorithm for probability distributions, right?
Yeah.
And that is, and how you do that is basically converting quantum state to a list of information on the complete probabilities, patch it, and then reconstruct the quantum state.
Yes.
And do you ever need like higher than second moments because I see like you have to you have to bound the error on the 2-point correlation function.
So like so I showed like the error, like in this rounding scheme at least, the error kind of goes down as 1 over square root of k. So basically you need to make your k to be 1 over epsilon square. So yeah, you need to go to higher than 2. because like the set you're conditioning on, that needs to be of size large. But it's an interesting question. Like, can you, like, is it okay to, is there a better technique that just lets you do this by just keeping like 2.2 local marginals? I'm not sure. At least not if you follow this correlation rounding, but maybe there are better things.
I see. Yeah, maybe we can talk about this.
Yeah.
And I guess another question is, what is the intuition that this problem is easier for dense graph? It seems like, well, at least one thing that perhaps I catch on, but maybe this is not the right intuition, is that the error budget, that if the graph is a complete graph, so you have about n square pair of things, the total error budget would be about around like 1/. Right.
So the error we're getting is like
epsilon.
Epsilon. Yeah, the error is like epsilon times. And I guess like the intuition is for these dense graphs is that, like, if you have like lots of connections, okay, every qubit is kind of connected to each other. In these kind of dense settings, you expect mean field approximations or product approximations to work pretty well. And so we know that mean field theory works if you make your lattice dimension very high, which corresponds to having like this kind of all-to-all couplings. So that's really why, like the Brandau-Harrow results, for instance, they show that product states give you good approximation to the ground state energy, or these kind of approximations. And product states are just like your mean field states. So that's like the idea why we think that this could be easier, because like if one qubit is talking to every other, you cannot have like a huge amount of entanglement between any particular pair. Like all the entanglement share across any edge will be sort of small. So you can like kind of approximate things by a mean field. So that's the intuition. But the annoying part, like as I was talking about in this, that the final question slide had, is that at the end you don't get to like we round to this very complicated looking thing, which is a mixture of almost product states. So I was trying to play around, like, is there a direct rounding to a product state? But yeah, it's hard to show.
Mixture almost product state. So this is there. So is there like some definitive thing in there?
Sorry?
Is there some like quantum definitive thing in there?
This is like, it just relates to this quantum definity theorems. So like the Brandau-Harrow paper has a section on like quantum definity theorems.
I see,
because like you're choosing this set C. Oh, so I didn't mention, like, it's like, so the closeness that you show in these marginals, it's like, it only happens if you choose this set C randomly, and then you average over all possible choices of it. So it's like you're exchanging it. So that's why that definity thing comes in.
And I guess the usual, or at least the basic definitive thing is just the mixture of product density matrices, or?
Yeah. So I just show you, like, I go back to the previous slide.
Could you show this almost product thing again?
Yeah, let's see. What did I have? Yes, so this is like what the distribution looks like. Okay. Now imagine applying like lambda inverse to this, and you get some rho, rho on C here. And then, this part is a little trickier. It's sort of like what you will get here is what is it? It's like the post measurement density matrix. Like once you do the measurement on C. No, wait, sorry, I'm saying this wrong. Okay, what you'll get is look something like, you have so here we're doing this random Pauli measurements. So you have the projector corresponding to some measurement outcome here, tensored with the post measurement state on J, and just the tensor product of that. And then you have like a sum over all the possible projectors, okay, on your C. Then you average over your choice of the set subsystems C, and then you average over the size of your subsystem, which is M over here. So you average over literally everything possible, and then you will see a nice cancellation in your mutual information, which is just, it's a really nice combinatorial argument. It's like this, it's very bizarre. Because it's just like it's screaming. It's basically saying that you get to like a mean field approximation, but you have to go through this condition.
Yeah, this is very interesting because for some reason I'm also thinking about conditional states. Something
nice. That's cool. We have been looking into some of this approximate Markov properties. I mean, I've been trying to read up some papers like Renner, Fernando Brandao, or like trying to extend maybe our result. It's pretty interesting.
Yeah. All right. Yeah. Should we? Yeah. So I guess that would be the end of our official if Colloquium talk this time. Yeah, thank you, Anirban, again, giving an excellent talk at this time of the day. And well, yeah, I hope we can see you again in some opportunity in the future.
Sure. Yeah.
Yeah. Thanks a lot.
Thanks.
Thank you for the audience as well. Yes, I guess we'll see you perhaps in the next if Colloquium or TAPO seminar. Thank you.